So, hi everyone, welcome to this, our 41st Inspiration Exchange. I'm super excited for today's session. Really, it's trying to cover areas around reliable machine learning and how do we ensure trustworthy machine learning. And the real topic is around AI model evaluations and deployment. Before we jump into the session, I just want to highlight that the Schaar Lab at the moment is hiring for PhD positions. So these are 5 fully funded positions. So please, if you're interested, apply to the lab. Mihaela would be delighted to see your application. And then before jumping in, just to highlight our upcoming sessions after the new year. So that will really cover clinical co-pilots to democratize machine learning for healthcare, and that will take place on the 13th of January. So we hope you enjoy today's session and join as we resume next year. But then just to cover today's session, so today in the first part, we'll have a short introduction by Professor van der Schaar. Thereafter, we'll set a little bit of context with 2 short presentations on AI evaluations and deployments, 2 recent papers that will be presented at NeurIPS 2024 next week from myself called Context-Aware Testing and from my colleague Paulius on self-healing machine learning. And please post any questions that you might have for both the speakers, but also our panelists who I'll be showing next. Please post them in the chat, and we will be definitely happy to take those questions. And then finally, once we through those presentations, we're really excited to have a fantastic roundtable and Q&A with Dr. Jessica Schrouff and Dr. Grimaw Abebe Tadesse. I'll introduce our amazing panelists in much more detail when we get to the roundtable. So without further ado, let me hand over to you, Mihaela.
Yes, so hello everyone. I'm absolutely delighted that you have joined us today because this is a very exciting session for me. As you know, around 2 years ago, we started this manifesto in which we unravel this reality-centric AI agenda. And we really believe that we need to have different ways of thinking about AI if it is to make transformations for the good in the world, whether this is in healthcare or other domains. And as part of this, making AI really work in complex environments is a key point. And we know that machine learning has often been brittle and failed when taken to the real road of reality. So what I really hope that we are going to do today with some fantastic presentations of Nabeel and Paulius, but also through our roundtable discussion, is to convince you that there is more to machine learning than just developing the next algorithm or the next tweak or an algorithm. That what is extremely exciting is to understand how algorithms that are developed already could be better tested, could be better understood at deployment time. And how can we really put machine learning within a framework of thought that enables us to build the inherent resilience, robustness, and efficacy that we need to prove to the world if it is to use machine learning in complex domains such as healthcare. We often get very excited as a community when a new type of algorithm appears. But I'd like to ask you to really pause a little bit and see, isn't it going to be equally exciting? And maybe at this stage in the machine learning trajectory, even more exciting, to provide new ways of thinking about how AI needs to be tested, how it needs to be deployed, how it needs to be embedded within larger ecosystem of other tools that we want to put together to build this reality-centric, let's say, applications. So I hope that today you are going to enjoy this, and I hope that we will collect some converts to the area of AI deployment, AI testing. We need very new ways of thinking, and it requires novelty and it requires creativity. And I hope that you are going to be excited about this and see this area of AI testing and deployment no longer as an utilitarian area, but rather as a very impactful, cutting-edge area in ML that I think it's underserved and requires new brains and new ways of thinking.
So hi everyone, once again, my name is Nabeel. I'll be talking about our paper called Context-Aware Testing, a new paradigm of model testing with large language models. This will be presented at NeurIPS 2024. And this was joint work with my great co-author who you've just seen, Paulius. along with Max Leuten and Mihaela van der Schaar. So we really know that in the real world, machine learning models do actually fail. We do have really good models, but when we really take it to the real world, models actually fail. And this is really the case that despite us showing strong average performance, models often fail for different reasons, whether we take them across distributions, and a focus of this paper is often on subgroups or slices of data. And this can lead to harm when we're deploying such models, particularly in like mission critical settings like healthcare. And really the idea is then comprehensive model evaluation is then very vital to surface these systematic issues and really brings to the fore the ideas of how should we even be testing in the first place and what should we be testing for. So the core takeaways of today's presentation before getting into it is really we hope you take away of how should we actually be testing in the first place. And the problem that we tackle in this paper, context-aware testing, is that data-only testing methods, so these are testing methods which take data as the sole input, often miss important testing dimensions. And this is particularly important because we assume even if we are testing machine learning models, some of these poor testing practices become widespread, and yet we still have unreliable models, even if we test. And the solution that we propose in this paper is something called context-aware testing, and we believe this is very useful, as we show empirically in the paper, that we are able to consistently and reliably identify model failures much better than data-only testing approaches. So the core challenge really with current testing practices is really around reliability. Before we jump into that, we wanted to really answer 3 questions in the paper. So first is like, why do we even test in the first place? And we really thought that obviously we want to test because we want to understand system, and in this case, machine learning system failures under a variety of operating conditions that this model might be taken into. The thing is, how we're testing at the moment is what I've referred to as data-only testing, and this is either average testing or subgroup level testing, or otherwise known in the literature as data slicing methods. And what we refer to is we're testing with these data-only testing methods, but what we really want to get to is we really want to understand what dimensions we want to test for, and then actively seek out failure cases in ML models. So why do data-only testing methods actually fail? And the basic thing that we come to is data-only testing methods are really prone to missing important testing dimensions. So we've really got 2 types of data-only testing methods. So the first is what everybody is probably very familiar with, and this is what we refer to as average testing. So you've got some sort of holdout data set, and you evaluate your model and produce some sort of average performance metric. So this doesn't seek out actual failure cases in your machine learning model, and you might be really masking unreliable model performance. So you might have very strong performance on average, but you might be masking the fact that the model underperforms in certain systematic areas. Data slicing methods really try to get to the heart and address this problem. However, they only operate on raw data alone without accounting for problem context. So as you'll see in the paper, there are various different data slicing methods, each with different approaches to how they do the slicing mechanism. But overall, all of them still need to account for this large space of potential model failures. And what we formalize in the paper is when we actually do these evaluations of different data slices, we should actually be looking at this through the lens of hypothesis testing. And what do I mean by this? So every time we take a test or a subgroup and we run a test to assess performance, this is equivalent of doing a hypothesis test. And the problem with this is because we evaluate this very large space of potential failures, we conduct many, many hypothesis tests, which leads us to the multiple testing problem. So where these data slicing methods then are really prone to false positives because we evaluate many subgroups, even if we do correct for these false positives through different correction mechanisms, we then prone to false negatives because we don't prioritize likely failures. And even if the first 2 are not even as much of a consideration, the third is an issue where we don't actually search for meaningful failure cases. So we actually might get subgroups which do have underperformance, but with respect to meaningfulness of the actual application, this subgroup that you found is actually unactionable from a practitioner's perspective and is non-meaningful from the actual application perspective. And the question we try to answer in this paper is how can we address many of these challenges? And for this, we propose the paradigm of context-aware testing, where we use context to guide the search for meaningful model failures. So really to address these false positives, we use context to decide what data slices are worth testing in the first place. We then address this issue of false negatives, of using context to prioritize tests which we should perform first. And then we also address this issue of meaningful failure cases by using context to filter out failure cases which are either meaningful or not. So we more formally describe this in the paper, where this is just a tiny snapshot of the more formal definition of context-aware testing. But for this presentation, I'll just show the short snippet, which is really context-aware testing is composed of two steps, where it's first defined by this idea called a context-guided slice sampling mechanism, pi. So this function pi would take in some sort of context C, your data set, so your maybe XY pairs and the number of tests you want to conduct. And we actually use the C, so the context, as some sort of inductive bias for some slice sampling mechanism pi to prioritize slices which might actually contain meaningful failures. And then once we've got these slices, we then have a multiple hypothesis testing procedure to actually validate or falsify whether we actually support the hypothesis or we can reject it. And we define a meaningful failure, which is characterized by statistical significance and practical relevance. And you can take a look at the paper for more of the mathematical definitions that we've structured to define this area of context-aware testing. You then might say, how do we actually go from, for example, this pi that you've shown, this high-level concept of a context-guided slice sampling mechanism, what does it actually mean in reality for me? So we instantiate pi, or this context-guided slice sampling mechanism, with something we call smart testing, which is the first tabular context-aware testing method. And smart does this by employing a large language model in 4 different ways. So the first is for the task of hypothesis generation. So we use a large language model to generate multiple hypotheses of where the model is likely to fail. And we know from scientific theory that we want to actually propose hypotheses and actually invalidate them. So this really naturally fits with that. Then once we have these hypotheses, we move on to something called the operationalization step of what do these hypotheses actually mean with respect to real data? So how do we explicitly define these hypotheses? And then once we're able to explicitly define them, we can then take them to real data to evaluate and basically self-falsify the actual hypotheses. So either accept the hypothesis or reject, which in this case, is that this data slice that we have is systematically different in performance from average performance. And then this also allows us, using a large language model, to create clear model reports. So to give you an example just of the output of our system, so let's say take the case of a healthcare prediction model. So let's say we have a hypothesis of elderly patients that the model is failing. We're able to produce a justification of why this makes sense for this hypothesis. We're then able to take it to real data and operationalize what elderly patients actually mean with respect to our data set, which is an age above 72. We then run the hypothesis test itself and produce that the performance is different with a very low p-value, and we can accept or support this hypothesis. What's actually most interesting is this broader LLM system is really orchestrated end-to-end in an automated way to actually run this whole step. So as you can see on the screen, we're able to take in a data set, and whether you do have external input, so this might be human input, but it's not necessarily required. All we require is a data set. We then have the hypothesis generation step, which is not just once off, let's prompt the language model and get hypotheses. We have a good set of reflections where we have a process where we can ensure we have good, high quality and stable hypotheses. So this is the self-reflection, self-refinement that you can see on the screen. Once we have those good sets of hypotheses, we then have this operationalization and falsification step, and then a final model evaluation and report generated. And what's nice is that all of this is executed automatically by a large language model, additionally as the orchestrator. And what Smart really provides is an interpretable way, finally, to really test machine learning models, because we have this evaluation that pops out at the other end. So just on some results, so even if we don't care about false positives and false negatives, the main thing we really firstly care about is, do we find the subgroups where we perform the worst and where do we have the highest performance discrepancies? And what you can see compared to very many alternatives from the literature and across various different machine learning models, we're able to identify groups which have the highest performance discrepancies. So these are the groups where models deviate the most from average. So this is the first case. Secondly, smart really has these very much reduced false positives. So taking an example, as you can see on the screen, so a lone default prediction task, as we introduce a huge number of irrelevant features into our data set, we look at which methods pick up fewer irrelevant features in their actual slices. You can see smart at the bottom of the screen in gray really isn't sensitive to this because we're really guided by context. And these data-only methods, which actually look at all numerical numbers just as numbers being introduced and can't actually reason over the fact that some of these are actually irrelevant features to the actual task, actually pick up many of these features quite a lot. And we have a huge amounts of false positives starting to get picked up in many of the slices. Additionally, Smart also has much lower false negative rate. So this is really important when you think of using a large language model, where somebody might say there's some sort of biases in the language model that actually might be introduced into our testing procedure. We actually systematically assess this, that does the hypothesis proposition and refinement step, as well as self-falsification, help us avoid these false negatives, which might come from biases. And actually, we want things that reflect real data. And we see once again, as we introduce different levels of false negatives, we actually at a much lower rate than many of the other methods across the literature. And then finally, we've done many comprehensive experiments beyond what I've shown you, really to highlight the benefits of SMART. And I'll just highlight a few, and we encourage you to take a look at the paper. We've looked at many dimensions, which is including like evaluating robustness to LLM biases. We looked at how does SMART fare depending on whether you're using like GPT-4 or open source LLMs. We looked at sample size sensitivity and how this testing procedure might work if you want to evaluate performance as you move, say, across different deployment environments, across different places. So we encourage you to take a look at many of these different experiments that, given the time, we can't delve into all of them today. And with that, thank you so much. We hope you'll take a look at the paper, and please reach out on the chat if you do have any questions. And I'd like to hand over to my colleague Paulius, which is really a great follow-on. Now that we've detected that a model might be failing, how do we actually adapt it?
Good. Okay, so I'll be presenting our work on self-healing machine learning, which is a framework for autonomous adaptation in real-world environments. So I'm Paulius. This is work done together with Nabeel, who we just heard of, my fantastic co-author, as well as Schrouff and Mihaela van der Schaar. We'll be presenting this work at NeurIPS 2024. And the fundamental question this paper asks is, how can we build machine learning systems? And in this paper, we focus on supervised learning models that autonomously adapt to changes in environments. So that's what this paper is about. So if there's one slide you'll remember before you doze off, it's this slide. So this is important. So what's the core takeaway? So the problem we're solving is that current approaches to addressing drifts, so drifts meaning that your model becomes worse over time, they typically rely on predetermined actions. For example, you see that a model is now performing worse than today or than yesterday or a week ago, and you trigger retraining or you reuse an old model. And so you have a fixed set of actions, and this can lead to suboptimal model adaptation if the kinds of actions you're considering are not really optimal. So the solution we propose is self-healing machine learning. And the idea behind self-healing machine learning, the fundamental principle is that before you adapt, before you propose an action, you need to consider why is it that the model has degraded? You need to diagnose the problem, and on the basis of that diagnosis, propose the best corrective action. So this is the core takeaway, and I'll be diving into this presentation, zooming in into these different parts. So let's consider this nice illustrative example. So on the x-axis, you have time. On the y-axis, you have accuracy. And so suppose you have a model that's constantly making predictions about anything. So for instance, I used to work in a bank. So let's say you have a model that's making bank transaction fraud detection. So is a transaction fraudulent? So you're trying to flag it, and it's a lot of hard work. You want your model to be working as good as well as possible. And over time, you have some stable performance, and something happens. And so suddenly you have a drop in performance. So now you're at today. What do you do? And suppose you have 4 actions. So action 1 is you can retrain your model on the most recent available data. Action number 2 is you might add new covariates. Action 3 is you might reuse an old model from last summer, for instance. Action 4 is you might start using combinations of different models. So which one is the best one? And to us, clearly, we would think that we need to understand why is it that the model has started to degrade. Why is it that there's this drop in performance? And on the basis of that, we should choose the best action. So if, for example, these fraud techniques have started to change in some ways, perhaps we need to add a new interaction term or a new covariate. If there's a massive drift in the kind of behavior, perhaps retraining the model in new data is the best possible thing. However, perhaps the new data is extremely noisy. There's very little of it. And if you retrain the model in new data, you might have very high variance estimators, which might be optimal. Perhaps then the strategies that now these fraudulent people are using reflect the strategies you have a year ago. So again, if you're just retraining your model in new data, you might not be employing the information you already have. So to really understand what it is that the best strategy is, you want to, first of all, understand what's happening. So the reason why you just cannot rely on predetermined actions is because each thing you do implicitly has some assumptions about it. It presupposes some stuff about the underlying data generative process. So for instance, if you retrain your estimator on new data, you're assuming that the new estimator on at this new time point, this new model that you've trained, is better than your previous estimator. Now, there are many cases when this is not true. If your new data is corrupt, if your new data is noisy, if your new data contains just very few inputs, if your new data is somehow not reflective of the data that's going to be coming afterwards, all of these mean that the model you're now going to be using, retraining on this new data, is not going to be the best possible model. If you decide to reuse an old model, then what's going to happen is that you're assuming that past models are still relevant. So in all cases, whatever action you do, you're presupposing something about this data, the data generative process. And that's not bad. Any kind of adaptation action implicitly presupposes some assumptions. You implicitly, in some capacity, assume that you know something. So the question is, what is the best thing you can do? What is the best thing you can actually presuppose? And we argue that the best way to do this is to have a diagnosis step. So this is where self-healing machine learning comes in, and it involves 4 steps: monitoring, diagnosis, adaptation, and testing. So this idea of self-healing machine learning, it has its origins in many different systems. So in the cold era, there were various fault-tolerant networks that were designed to survive nuclear attacks, and they were self-healing systems. A lot of people are using biomimetic materials and autonomous technologies, inspired by how nature, in some cases, is able to repair itself. So this idea of self-healing in itself isn't entirely new, but its application to machine learning is novel in terms of model adaptation. So we took this idea actually from military context. So in the Cold War era, there was a push for self-healing systems during the Cold War when there was a need for reliable systems, and especially in the US military. And there were a lot of initiatives called, for example, the Defense Advanced Research Project. They explored a lot of autonomous and resilient systems, and then this didn't come out to work for the machine learning community. So here we are bringing the self-healing component to the machine learning world, and we're formalizing it in 4 steps. The first one is monitoring. So has the performance of the model decreased? And you can implement this via a simple statistical monitoring algorithm that simply monitors, is your estimator somehow decreasing or not? The second step is understanding what are the reasons for this decrease in performance. The third thing is, once you've understood its reasons, how can you best adapt or heal the model for it to go back to your prior performance levels? And then the fourth one is, you want to understand if your adaptation strategy is actually useful. So you want to test those adaptation strategies and then deploy the best one. So we formalize everything in how it actually directly relates to machine learning models. And the goal of self-healing machine learning is to select an optimal action to best adapt to the new data distribution. So you can think of a set of actions that you can take. Action 1, create a new covariate. Action 2, retrain your model in new data. But there's so many different actions you can take, actually near infinite actions, because there are near infinite data points you can choose, and near infinite covariates you could add. And your goal is to select the best possible action that could minimize your function or your estimator on this new data distribution. So of course, this action will inherently depend on this diagnosis step. So the question is, how can you actually define the diagnosis? So I'm not going to go into too much details here. I'll leave it for the paper. But in the paper, we define very rigorously what does it mean to understand why the model has failed. We define things like the certainty of the diagnosis. We define something called an optimal diagnosis, which we say, which has some specific properties. And we use those definitions to derive some nice theoretical properties about what it means for you to optimally adapt. For example, we find that your optimal diagnosis will always have zero entropy under some assumptions. So we build a whole theoretical framework that we think can be extremely useful for enabling practical applications. So I'll leave all of this theoretical part for you to read up in the paper. But then on the basis of that, we build a concrete self-healing system that we call HLLM. So HLLM is a conceptual self-healing system that contains 4 components. Let me just maybe get a laser pointer. Nice, okay, we have laser pointer. So you have a statistical monitoring algorithm. That means it's some sort of algorithm that constantly checks, has your model's performance started to decrease? Once your model's performance is detected that it has decreased, then we go to the diagnosis step. And in HLLM, this specific self-healing system we've constructed, we use a large language model to directly try to diagnose why is it that the model has failed. Of course, we're never going to know for sure, but we use the principle of abductive inference, which means inference to the best possible explanation. We provide into our system a set of information, everything that we have about the system, and we come up with a set of 10 or 15 different hypotheses about why is it that this model could have started to perform worse. On the basis of that, we go to our policy pi. Our policy pi is also implemented as a separate language model, and it takes in each specific diagnosis and detects then that for each diagnosis, if this is the problem, this is the best action we can take. And again, these are simply proposals from a specific policy that might be optimal, might not be optimal, but we're implementing them, in this case, via an external language model. And then a testing module, which gives a scalar number or like some sort of value as to how good each action is. And this value is important because you might, for example, say, if this is the problem, maybe the best adaptation strategy is to retrain your model in new data, and then suddenly that doesn't work out or that's suboptimal. So then you would discard that and you would go to the next point. So of course, there are many different design choices you could make here. So I'm not going to talk about how do we implement the testing component, how do we exactly implement the policy pi, but I'll leave it for the actual paper. Let me now remove the laser pointer. Here we go. And so we do a lot of experimental results. We look at how our system performs across a whole bunch of different setups, and we analyze the effects of different components, and we find that it's consistently useful, and we try to understand why is it that it's useful. So again, we'll leave the experimental results for you to check out in the paper. But so fundamentally, we think this is a very important framework for building self-healing systems, where we want to move from an era where we're adapting models blindly, we're shooting darts in the dark, where we're not really sure if this action is directly addressing the root cause. And we want to go to self-healing systems, where self-healing systems try to understand or infer in the best possible way we can, why is it that there are these changes in performance, and on the basis of that, propose the best possible things we could be trying and iteratively adapting, trying to see if the adaptation is optimal. So we think this work is really important and very happy that we've managed to share it with you. Thank you.
Awesome. Thanks so much for that, Paulius. And with that, we'll be moving to the panel discussion. And just give me 1 second to introduce our fantastic industry guests today. I think we've got 2 really great guests who've done a lot of work on very relevant topics, both on like the adaptation side as well as on the model testing side. So I think we've got fantastic panelists today to unpack all of this today. So I'll first be introducing Dr. Jessica Schrouff, who is a senior research scientist at Google DeepMind, and Dr. Grimaw Abebe Tadesse, who is a principal research scientist and manager at Microsoft AI for Good Lab. Super excited to introduce the both of you. Thanks so much for taking the time, and we're really keen to hear your opinions on this topic and how we can really push this forward and drive this agenda. And Mihaela, I believe you have questions to kick us off.
Yes, so thank you again, Jessica and Girma, for joining us today. I wanted to ask you, what do you think about this, let's say, let me call it almost like a paradigm shift between just focusing on building more and more powerful models but at the same time wanting to bring these models from the lab to really complex real-world scenarios. Do you think that this is something that's more utilitarian in nature? Do you think that this is an entire research agenda that we may need to pursue as a community if it is to build models that are really robust and resilient and operate well in the real world? And if so, what are the challenges that you think are most exciting from a research perspective, and which challenges are more important from a practical perspective? Jessica, maybe I start with you.
Sure. Thanks so much for having me, and thank you for a great discussion and the presentations. So in terms, like, it's actually interesting because I do not come from a machine learning point of view. My background is more in applied machine learning for neuroscience, and especially neuroscience discovery. So even in 2013, when most of the community has actually started to move towards more like deep learning, and like NeurIPS would be full of papers on deep learning, I actually was still working with support vector machines because like neuroscientists wanted to understand what is happening in the brain. And it was really interesting because in a way that was, the first dabs at, interpretability. And it didn't have that name. So in a way, I've never actually been inclined to think that bigger models or more powerful models will just solve everything. I don't think, I'm not convinced that there will be one model for all problems as well. So like, to me, this area of thinking around, like, from the design of the problem to like, and that comes with a lot of choices we're making already, to how we end up in the actual deployment, and really thinking about across all these steps, to me is very crucial in our field. And I know there's a lot of kind of like parcellation that's going on with like, oh, one team does like, like pre-training, then another team does like, post-training. And then we use large language models as like, like some black boxes, and we don't really, we kind of ignore what's been going on in them. And I feel that, like it's going to make it actually quite tricky in the future to really address issues of generalizability and safety. Fairness is a domain I work in particular, and things like context matter extremely, and what you do in the end. There are a lot of discussions around, utilitarian, and I think maybe there are some steps that will need to be if we want to start showing the potential for AI to make change. But at the same time, I still want to like make sure that we don't necessarily lose the bigger picture, and really think about like, also, how can we make our society better? And I'm again coming more for the fairness side, and thinking about are there, feminist or anti-racist technologies that we can actually build and deploy with this really like with this aim of targeting like challenges in society today. And that can come in healthcare. I think especially in healthcare is quite relevant, but also in a lot of other domains.
Wonderful. Grimaw, your thoughts on this whole area, and is it exciting? Is it exciting from a research point of view? What will be the research questions, and more generally, your thoughts on the agenda?
Thanks, Mihaela, for the invite. I'm glad to be here. Great work, Nabeel, Paulius, really. I'm sitting in Nairobi, Kenya now, for context. And at AI for Good Research Lab, often the projects, the problem we work actually came from partners on the ground, whether Ministry of Health, whether nonprofits or UN organizations. And I really enjoy the conversation today because there is there has been a lot of context missing in the way we develop ML models, especially for healthcare. Mihaela, you mentioned, how do we make it happen, AI in complex setting? I would imagine healthcare is even more complex, given the different contexts we have across the globe. And this is a kind of conversation we need to have, and I'm very excited about it. Something I was thinking as well when Nabeel mentioned context is we always go for those quantitative evaluations for holdout validation, especially for predetermined subgroup analysis. But there are other contexts, as you said, more than even the data. Given if we think about taking the solution outside the lab into the hands of decision makers, policymakers, their context is even different sometimes. Their priorities are even different. And we don't usually consider that in our evaluation pipeline. And in addition to, of course, generating the hypothesis, the Ministry of Health in Kenya versus the Ministry of Health in South Africa, they have different priorities. They have different contexts. They have different resources to accept your machine learning model, to deploy them to really augment their decision making. And this is a step in the right direction to open up beyond the data. There are other contexts that could even vary across space and time to be included in the evaluation of the model. But going forward, I have also two still concerns, given the evaluation, the way we use LLMs to generate the hypothesis and to automate some of the intermediary steps. But I am from the continent, still language models are perceived as not really reflective of the nature here in the continent. But now if we put them with their still concerns and biases, and so to automate the self-healing or generating context, that will be definitely more to evaluate going forward. But as well, the practicality of healthcare in different contexts, if you think about multimodality, time series, tabular, all others, and I would love to see the evaluation of ML models trying to encompass across the actual nature of healthcare data, which is often multimodal going forward. So let me stop here for more discussions, but again, these are my initial statements here.
Well, thank you very much, both of you. Jessica, maybe I go back to you for a follow-up question. So you mentioned use of machine learning to solve real-world problems in a totally different domain and a complex domain of neuroscience. Often we think in machine learning, I think, wrongly about data. The data is just some data set that we have, and we often believe in machine learning that everything is about this data set. But the reality is that collecting data, thinking about the role of data in both training the models, but since the focus of the discussion today is more about evaluation, validation, testing, how do you think really we should think about data from a problem point of view? So AI, like you rightly said, is often a supporting tool. It's not a goal in itself. It's aimed to empower neuroscience, healthcare. We have two settings here. How shall we think about collecting data and thinking about data and data sets if it is to build more robust models beyond just the training phase? And shall we already at data acquisition time think about this subsequent step of validation or not? Any thoughts on that?
Yes, thanks for the question. Yeah. So I think the short answer is yes. To me is a bit in a way now becomes a bit more obvious when we think about things like fairness, because a lot of times you get a lot of training data with just covariates labels, get that into a training pipeline, and you're like, okay, now I want to evaluate fairness, and we don't have demographic characteristics. And that's just and we know that even if we do that, it's really just the top of the iceberg, because then you have to think, okay, well, what happens if, and that was the case, for example, with Dermicist, which was this model that based on the picture of your skin would determine if a lesion was coming from a certain disease or not. So really trying to make a diagnosis. And they were conditions that were really rarely associated with, let's say, certain skin tones, like darker skin tones. And even the medical, clinical collaborators were like, well, yeah, but it like never really happened. So we don't really need to worry about this. But also like the medical field evolves. And now there have been like more specific targeted efforts, like afterwards, there needed to be those efforts to then really be able to evaluate, because before, on 5 patients, there's nothing you can say. And so like, what do you do with that? Like, do you then deploy the technology selectively? Do you just like delay the deployment? And this becomes a very difficult like ethical question as well, knowing that again, these are just like, very broad categories and very, again, just the tip of the iceberg, because it's just like an evaluation on data slices. It's not even thinking about what happens after you make that diagnosis. How is that going to impact the health system that it's going to be deployed in? How is that going to feed back afterwards? Can you deploy and then get that data later on? So I think all of these questions, it's really like key to think about them as we even think about like what problem do we really want to address? How is it going to disrupt the workflow when it's deployed? And what are the consequences for different subgroups, especially marginalized subgroups, as we go to with this technology? And even, is that technology the best technology we can get? Because sometimes you might have easier or simpler solutions, maybe hardware solutions that would give you potentially better solutions on the ground. And I think we need to like not forget that as well, that we as machine learning practitioners might not actually have the best solution.
Grimaw, a very different question for you. So given that we often evaluate the machine learning models in our top conferences in somewhat maybe non-rigorous ways, do you have any thoughts about, shall we come up with new standards of evaluation such that we make sure that the models that are built pass a certain bar? Or shall we put subsequent steps, maybe after a publication process, to make sure that these models indeed will translate to the real world? Do you have any thoughts about the process on how to take something that was published in a conference to the road, let's say, whether it's in Nairobi or elsewhere in the world? Do you see a spectrum of let's say, of validation or of stress testing of models? More or less, I often like to use this example from aviation, where we have these wind tunnels where we make sure that every component is tested and stress tested, and the entire product is stress tested before it even starts to fly. Should we have more rigorous practice on that? And if yes, how? And how do we do that without impairing, of course, the innovative process that the AI ecosystem currently is having?
I think definitely it goes without saying, subsequent evaluation of ML models is important for any setting, really. But a standard is always good to converge, but that becomes even, what does it mean across different contexts is still a question, but always great to have a standard any ML model needs to hit, so that it could be, green lighted to be deployed in practical setting. But if I could zoom in, always, I guess, we do research, we do innovation for an impact on the ground, really. And if we try to evaluate the importance, the necessity of those models and the supposed impact they're trying to make, that would be always great. I said that it's not easy, but if it's not making an impact, definitely we shouldn't put ML models just for the sake of, automating a certain pipeline. But that impact could also be different across different contexts, not only between Nairobi and Cambridge, but also Cambridge now and Cambridge after 5 years, right? So that's very important. But if I could zoom in into what Jessica already mentioned, to make research outputs, back into the society, back into the hands of policymakers, decision makers. I thought our job is always to support domain experts to augment and scale the decision making. And the evaluation is not only data. We have discussed for a few years already, data is a critical component of the pipeline, the subgroups that could be detected whether, predefined or automatically detected. That's good, but at the same time, I tend to be more concerned about even the problem definition, really. You asked Jessica what kind of data we need to collect, but the first question is, do we really understand the complexity of the problem on the ground? A specific ML pipeline for, could always be detect a particular disease or prediction whatsoever, but really, if you consider discussing with other stakeholders, starting from the healthcare, the clinician, the health ministry, all have their own different priorities, but the same problem, which is healthcare. That understanding of the problem is really very critical to make an impact. And that understanding also suggests what kind of data sources do we need to use as a primary source, as a secondary source, how frequently, how big, and all other variables we need to fit into the data. So I would say data is not the only thing, but at the same time, understanding the problem first is critical because it informs all the next pipelines about model choice, evaluation choice, validation choice, and even the kind of data we collect. Something we keep often forgetting is also the other contexts again, infrastructure and end user. You are developing the solution really for who and what kind of resource that user has at his hand to realize the impact we assume at the beginning of the conversation. So the usefulness or the goodness of the ML model is able to be characterized to deliver that solution in those contexts of infrastructure and resources. And at the end of the day, we said impact, but that could be different: time, money, resource. That could also be considered when we try to evaluate ML models just beyond the data.
Thank you so much, both of you. Nabeel, I'm going to give it back to you. Thanks so much, Jessica and Grimaw.
I think the question I really wanted to ask, and I think it follows up both from what Jessica mentioned and what Grimaw has just mentioned. So like these same machine learning models are going to be deployed in some situation. They're going to affect, like have almost this feedback loop. Like once we change something, it then affects new things, and we need to start working with stakeholders. And it was mainly the question that, so say we like an academic research lab, is that how do you both view this like academic, industry, government, stakeholder kind of collaboration, and how do you think we all could collaborate much better to do things which are like much more impactful? Because I guess there's like all these different partners doing a variety of different things, and like I was curious, how do you view getting this collaboration to work better? And I guess whoever wants to take it.
I could start, Nabeel. This is something I often try to do as an applied research lab, but still discussing with collaborators that come from different ecosystem, whether nonprofits, governments, and so on. I was in a panel in August, I think in Ishkai. Someone mentioned the complexity of developing AI solutions for an impact. The first layer of complexity is the science of it, the implementation of it, really. The second is the communication piece. You develop the solution. Do you communicate the right way for these diverse stakeholders so that you don't, you keep everyone in the conversation? The third one is, of course, the politics of it. Still, it's great to develop an AI solution for a particular healthcare problem, but how do we translate that win for stakeholders who have different priorities? For example, if you work with governments, I would say often the priority is how could I get elected next time again, right? And that is a priority. Of course, healthcare is also the priority. And this is what I mean by getting the communication right, getting to reach all different stakeholders and calibrate the conversation accordingly so that everyone gets win out of the solution we develop, so that that multi-stakeholder collaboration could be achieved. Other than that, if we develop research alone in an academia setting, it's very difficult to bring into practical decision makers' hand, especially if you consider at least Africa. The government still often has much of a saying in what happens in the country. I would imagine the same somewhere else, but you cannot avoid that multi-stakeholder conversation. But we need to make it happen. It may be sometimes taking longer time, but it needs to have scientists like you, the policymaker, the domain experts, that clinicians, to engage our service all the way in the process so that the solution we develop could be trustworthy for everyone concerned and potentially bring that impact at the end of the day.
I think that's really, really good advice, and like many pointers. I think that really crystallized it very well. I know we do have quite a few questions, I guess, from the audience, and I know Antoine had quite a few questions if you are online, and I think we can definitely answer the questions ourselves in the Slack. But I know for Jessica, Antoine, you had quite a few questions, so if you'd like to unmute yourself.
Yes. Did not let's see, my camera, is it on? Can you hear me as well?
Yes.
Can you hear me?
Yes.
Okay, thank you. Yes, so for Jessica, well, I'm just going to read my question to you. I really had two in this case. So I wonder if whether there's one monolithic master AI might boil down to semantics, as in how we define a system. So since if we have different models with very little communication bottleneck, then those could constitute a single system. So for instance, the brain might have multiple regions, circuits, and etc. So that's my first question. And my second question is a bit unrelated, but it's when you spoke of determining how disruptive a new AI would be to a workflow, how does DeepMind approach this? Does it develop with minimal disruption in mind? There is clearly a dilemma here in my view, but I wondered how you and your org treated this question. So thank you very much.
Thank you, Antoine, for the questions. Yeah, so the first question around this monolithic AI. So, I mean, yes, of course, there's a question of definition there. But even if we, like think about like the brain in a way, like, like we all specialize in different things. We all have our own like experiences and context. And in a way, like there will be, like, to me at least, there will be a necessity to give that information to like this monolithic model if we were, and find the right experts basically in that model. So yeah, there are discussions around, should we build one big model? Should we build multiple models that can communicate between them? And whether you actually then call that a single model, then again, question of definition, completely agree. But yeah, my view at this stage is like maybe actually having this like gigantic, maybe multiple parts model in some cases might be overkill. And also like in a lot of cases, especially if you think of like resource limited settings, will just not be that workable. Like even the cases of like deploying models now on smartphones, or on, Raspberry Pis, or simply, the cost of getting like, and the environmental cost of getting those models, like, will all be questions to me. I quickly answer your second because like I'm sure there are other questions for Grimaw as well. So the second question was around how to think about disrupting the flow. And yes, there will probably be a trade-off there, but there was and I'm going to like speak from my own experience, but there was this model that we were looking at deploying at the Royal Free Hospital, and we came with like this really nice like AI solution, and then actually like it didn't really work in the setting as it was, because basically in the hospital in the UK, you have like, they mostly have like these little computers on wheels that they go with everywhere. And so, and then they like have their own battery, but then they are like, then they fall apart, and then you have to like plug them in. And so basically having this like AI model that would give you alerts for if a patient was deteriorating was actually not practical to implement as it was. And you needed kind of a hardware evolution of people having, you know, like phones, or like a centralized unit that would monitor those alerts and then direct the teams. Like, and so that was quite a disruption in the flow. And I think that part probably took more time to really like think about than the development of the AI system. And yeah, and then in the end, you know, like it did not go through. But it was still a really, really interesting experiment of like, how can you even push change into a system, especially one that is as resistant to changes as healthcare, in at least in so far in the UK. But yeah, I'm sure there will be like maybe Grimaw also has thoughts about that. But
Thank you. Thank you so much.
I think actually quite related to that last bit is actually a question for Grimaw, and I guess I might, and I hope it's okay to the audience that I take a bit of liberty to merge two questions together, just given the time. So this would be Raghavendra's question and Antoine's question. So really it was around this idea that, of course, when you think of like robustness and performance of models in the real world, the model might not perform well. And I think it was a question to you, Grimaw, around two dimensions. The first is that, like, have you experienced situations where there's like, what challenges are there in data that limit a good AI impactful project? And I guess if so, does that mean we need to think a bit differently when designing model architectures and like training strategies to account for these like data challenges?
That's a great question, Nabeel. We often have typical challenges in data to make really an impactful AI solution that, you name it, a sparse representation, lack of, you know, especially when you think about global models. Lately, I have been working on geospatial machine learning models for agriculture type problems. And as you know, there are lots of data sources available from, you know, satellite imagery. And there are a few global models which claim to produce different agriculture products. When you validate it into the local context, usually they, even if they were reported to have a very good average global performance, when you bring it into Rwanda, which has a very different context to any agriculture system, even with Kenya, let alone with Europe and US, that definitely fails. And it's not a mystery to see that, because the global model didn't have representative data in their training pipeline, really. That's where, again, the context is important when we evaluate. It's not just that global performance evaluation, where it is going to be used, and evaluating that is very critical. But again, you mentioned the data challenges, you know, that diversity, the concept drift, the temporal drift are often the challenges here in Africa. But also, someone may say we have a lot of data, but labeling is also a critical aspect of it. You think you want to automate decision making, but you have the data, but you know, how do you get good quality label examples is always a challenge. And one interesting research question is actually, given the data, how could we get quickly such good quality labels to, you know, build that impactful and trustworthy AI solution?
Right. Thanks so much, Grimaw. I think that really answers both the questions that both the audience members mentioned, and I think both myself and Paulius had many more questions that we were really keen to chat to you about. So I think this discussion could go on for much, much longer, but we definitely don't want to keep you beyond the time that we've promised. And I know we've got some more audience questions that we'll take offline in the chat. I really just wanted to thank both you, Grimaw and Jessica, for really taking the time to join us. Like, I think I can speak for both myself, Paulius, and Mihaela. I think we really enjoyed the discussion a lot, and I think there's so much more we could unpack with the both of you. But thank you so much for taking the time.
Thanks, Max and Nabeel, Paulius. Pleasure.
And for everybody else, we look forward to seeing you at the next session in January. And both myself, Paulius, and Mihaela will be at Europe's next week. So if anybody is there, we'd love to chat more about either of these works. Thanks so much, everyone.
Yeah, thanks so much, everyone.
Thank you.
Many thanks.